What's up, guys? This is part 3 to my series on polynomials in Maths Olympiads. In this, episode, if you want to call it that, we're going to be covering long division and multiplication of polynomials. So let's get into it. First of all, let's go with division, because in my opinion, it's easier. One quick thing to note before we get started is that if you're not comfortable with multiplying like large integer numbers like 1248 multiplied by 3682, you're not going to be able, it's going to be very difficult for you to do this, because multiplying large polynomials essentially works the exact same way as this. In the same way, like if you're not comfortable with long division, so dividing like, let's say 136 into 17,362. If you're not comfortable with long division either, then I would definitely recommend, or if you're not comfortable with like any of these, just multiplying large polynomials or long division, multiplying large integers and long division with integers, then I'd recommend learning that first, because it works the exact same way with polynomials. So I'll show you what I mean now. So let's say we have two polynomials. So one of them is x cubed plus 3x squared plus, let's go 11x plus 7. And then we have another one, let's say 7x squared plus 3x minus 2. Now, you probably notice here that I've decided to line up the powers of x such that the same, this is x to the power of 0 here and x to the power of 0, but I don't include it because it's just 1 and it doesn't affect the polynomial. So I've decided to line up the powers of x, the same powers of x in the same column, because it just makes life easier in my opinion. So when we multiply large integers like 137 times 26, we multiply this with, we multiply the rightmost digit of the bottom one with all three digits here, and we do the same for this one. So it works the same way. So here we'd start with minus 2 times 7, which is just minus 14, minus 2 times 11x, that's minus 22x, minus 2 times 3x squared, that's going to be minus 6x squared, and minus 2 times x cubed is going to be minus 2x cubed. So that's the first one, and now we just repeat that for all of the other terms that we have in our polynomial. So what happened there? 3x times 7, that's 21x. So again, I'm lining this up in the same column as the x to the power of 1 that we have next to the minus 22 here, because again, it will make life easier when adding. It's just way easier to see. So minus 2 times 11x minus 22x. Oh, sorry. No. I'm getting confused here. I'll just get rid of these arrows. Minus 3x times 7, 21x. 3x times 11 is 33x squared. So it's going to be plus 33x squared. And there's a plus behind that. 3x times 3x squared, 9x cubed. 9x cubed plus, so we've done that one. And now we do the same for the last x cubed, last term, which is x cubed. 3x times x cubed is x to the power of 3x to the power of 4, sorry. We do the same for the 7x squared term, multiply that by all of the digits that we have there, and we'll have like, we'll have 7x to the 5 over here, plus like some other stuff. You get the idea. And then at the end, you just add all of these together. So you add those, add those, add those, add those, add those, add those. And that's your answer. So it works the exact same as multiplying large multi-digit integers. Very basic stuff. The next one that, or the next, topic we're gonna, or thing I'm gonna teach you is the long division of polynomials. So let's say we have x squared plus 3x plus 1 divided by, actually no, let's make it a bit more interesting. Let's go 2x squared here. Let's go 4x to the power 5 plus, actually that's a bit too complicated. Let's just start off easy. 4x to the power 4 plus 2x cubed plus 7x plus 2. Okay, so now we're going into the long division of polynomials. One important thing to note before we start is that this thing here is called the divisor. It's an O, divisor, and this thing is what we're dividing, right, by the divisor. So let's call the divisor, let's call it D. Let's call this thing here, I'm pretty sure it's called the dividend or something. Doesn't really matter, let's call that R. So one important thing to note here is that the degree of D has to be less than or equal to the degree of R. Because if you think about it, if the degree of this thing here is greater than the degree of this thing here, then it's like, it's not going to give us a fraction per se, but it's kind of going to give us the same thing, because that's like, if we use the, like a similar scenario with long division of integers, if we have like 1,362 divided by, or like something here divided by 1,000, doesn't matter. Something here is going to be, actually no, we have to make it smaller, don't we? 932. Having the degree of the divisor being greater than the degree of R in this case, it's essentially like having this. So in this case, it's going to give us fractions, because obviously 932 is less than 1,362. Therefore, 932 divided by 1,362 is obviously going to give us a fraction. So, yeah, if the degree of the divisor is greater than the degree of R, then it doesn't work, because if you think about it, it's like kind of going to give us the same thing as a fraction. It's not going to give us a fraction, but you can think of it like that. We don't want that. So that's just a quick condition, I guess. Let's get rid of all this. Actually, that's quite important, actually. Let's do that. So yeah, in this case, degree of D is 2, degree of R is 4. Condition is satisfied, meaning we can go ahead. So essentially what we're trying to do is we are trying to, you'll see what I mean by this in a second, but you can think of it as like, actually no, I'll start with just doing it and then I'll explain how I think of it later. Okay, so essentially what we're trying to do is we first need to divide the leading term of this polynomial R by the leading term of D, okay? So 4x to the power of 4 divided by 2x squared is just going to give us 2 times x to the power of, well, x to the 4 divided by x to the minus 2 is x to the 4 minus 2, which is just x squared, so we're going to get 2x squared from that. So our 2x squared is going to go here. And now, just like long division with large integers, we multiply this thing here by our divisor. I don't even know if it's called a I think it is called a divisor. I don't know like those kinds of words. I just know how to do it. But yeah, so multiply that and we get 4x, so 4, which is from 2x squared multiplied by 2x squared, 4x to the 4, plus 2x squared multiplied by 3x. That's going to give us 6x squared, cubed even, plus 2x squared times 1, which is just 2x squared. Okay, and just like the long division, just like long division with normal integers, we're going to be subtracting what we've got here from this thing up here. So we've got 4x to the power of 4 minus 4x to the power of 4. Those two cancel. So if you can see here, what we're trying to do is just get rid of like the largest term, or the leading term of each polynomial that we get. You like just continue watching and like you'll start to understand. So 2x cubed minus 6x cubed is minus 4x cubed plus 7x minus, well, I probably shouldn't have done this because this is like, can be difficult to see, I guess. But here we've got, let's just remove that for a second. Here we've got like a plus 0x squared hiding there, and then it's plus the 7x. So if you think about it, we've got 0x squared. Well, we don't include it because it's 0 and it doesn't affect the polynomial. But we've got 0x squared minus 2x squared, which is just minus 2x squared. And then we've got plus 0x here, plus 0. 7x minus 0x is just 7x. 2 minus 0 is just 2. And we get this thing here. Now we're going to do the exact same process. So let's just get rid of this really quickly. And let's get rid of that. We don't really need that anymore. So we're going to be doing the leading term of this, because we've already got rid of the leading term of this. So now we need to do the like, I guess like the next greatest term, if you see what I mean, divided by the dividend again. So we get minus 4x cubed divided by 2x squared, which is going to give us minus 2x to the power of 1, which is just minus 2x, right? So that's what we're going to get here. We're going to place that there. And well, the reason why we do the leading term is because immediately as we multiply like what we've got here by the dividend, we are going to get, well, we're just going to get the, well, if we multiply this by the leading term of this, we're going to get the exact same as what's here, because if you think about it, we've just divided this by this to get this, and now we're multiplying this by this to get this, right? So we cancel it out because we get the exact same thing, which is, well, minus 2x over here times the 2x squared here is minus 4x cubed. And then we multiply minus 2x times plus 3x, which is minus 6x squared. Minus 6x squared, yeah, that's correct. And then we do minus 2x times 1, which is just minus 2x. And then, so yeah, we get here that, well, because all of this is being subtracted, this negative sign flips into a positive one, which means that, well, negative 4x cubed plus 4x cubed is just 0 because it cancels. So that's 0x cubed. We don't need to include that though. Minus 2x squared minus 6x squared. Oh, sorry, minus 6x, because that actually turns to a plus as well. So minus 2x squared plus 6x squared is 4x squared. Minus 7x minus 2x is plus 9x. And then, well, there's a plus 0 there actually. Plus 2 minus 0 is plus 2. And then we just go and repeat the whole thing, or sorry, repeat the same thing again. So we get 4x squared over 2x squared that we have here. And that gives us just 2. So we put plus 2 there. And then if we get rid of that because that's no longer relevant, we multiply this by this again. To get, well, 2 times 2x squared is 4x squared. So again, like the whole purpose of this is just reducing the leading terms until we get a what's called, like, you can call it a residue or remainder, whatever you want. I think remainder is like more intuitive because it doesn't matter. Call it what you want. Then we get, I'm going to call it a remainder. Then we get a remainder which has a degree less than this. So we just get rid of the leading terms until the degree of what we get is less than the degree of this polynomial here, which in this case is 2. So 2 times 2x squared, 4x squared, we've already established that. 2 times 3x is 6x. 2 times the 1, that's just plus 2. That's convenient. So, well, subtracting all of this from this thing up here, which gives us 4x squared minus 4x squared, 0. 9x minus 6x plus 3x, and then 2 minus 2 plus 0. So we've got 3x here. Now, as you can see, we cannot repeat this process here because the degree of 3x is 1, which is less than the degree of 2x squared plus, like, whatever that is, which is 2. The degree of that is 2. So this is our remainder here. Remainder. I think all of this should be right. If, like, the arithmetic or, like, multiplication or division, subtraction, whatever it is, if it's not correct, I apologize, but I could, as long as you understand what's going on, it doesn't really matter. Like, obviously it does matter if you get it right or not, but if you understand what's going on, that's probably the most important part in my opinion. So this is the remainder that we've got here. Now, as I've already stated, the degree of the remainder, let's call the polynomial representing the remainder, let's call that r. So the degree of r is always going to be less than the degree of this thing here, which is the divisor. So if we call the divisor, if we call that g, we call, actually no, let's put it into, like, nicer letters. Let's call divisor g, this thing f, remainder r, and then what's up here, what we got from the long division process, and we call that let's call that the quotient, which is q. So the degree of r, which is the remainder, is always going to be less than the degree of g, which is the divisor, I think. Does it make sense? You're dividing by... Yeah, that makes sense. You're dividing by the divisor. So, yeah. Degree of this is always going to be greater than the degree of the remainder, because if you think about it, if the degree of the remainder is the same as, or, like, even greater than the degree of the divisor, that means that we can continue the long division process. Imagine, it's not, but imagine the remainder is actually 3x cubed plus 2x squared. I know it's not, but just imagine. If that was the case, then we could still do the long division, we could still perform the algorithm one more time, because the degree of g is less than the degree of this, which means that 3x cubed will divide 2x squared. You understand? I know it gets a bit messy because of fractions, but whatever, you know? So yeah, that's very key. The degree of the remainder has to be less than the degree of the divisor. From this, we can actually also derive a nice little formula, or it's not a formula really; it's just an equation. So essentially, we can say that, well, this thing here, q, times g, plus the remainder divided by g is equal to f. So, like, okay, just like, okay, I'll just write it down and then explain. So we've got here that 2x squared, like by what I just said, 2x squared minus 2x plus 2 multiplied by g which is 2x squared plus 3x plus 1, and then that plus the remainder, which is, oh wait, it's not 3x. Let's get it back to how it was. So it's just 3x, yeah, plus 3x divided by 2x squared plus 3x plus 1. Okay, so this is what we get. Q, or the quotient, times the divisor plus the remainder divided by the divisor is equal to what we were originally trying to divide, which is 4x to the power of 4 plus 2x cubed plus 7x plus 2. Yeah, so that is what we know, and yeah, that's it, I guess. What else did I want to cover? Hold on, let me think. Oh yeah, sorry. So we can create a general formula for this, which is that for any polynomial division, we have that so for any polynomials f and g, f divided by g will equal some quotient, say q, multiplied by g plus a remainder, r, divided by g. Oh wait, no, sorry, I've messed that up. Have I? No, I haven't. Have I? Yeah, because that wouldn't make any sense. Sorry, I've messed that up. For any polynomial division, f divided by g, we are always going to get the quotient times the... yeah, well, I think I was right, yeah. Quotient times the divisor, which is g, plus the remainder divided by g. That just doesn't look right. Hold on, give me a second. Wait. Wait, what? Hold on. Oh gosh, sorry, what am I saying? I'm being so stupid right now. I'm so sorry. F divided by g is equal to the quotient plus... I don't know why I put the quotient times g. What was I doing? Sorry about that. It's just the quotient plus the remainder divided by g. Okay, now we can... Well, I mean, yeah, if you think about it, like, for any normal division, let's say 13 divided by 2, that's going to be some quotient, which is like, or some like whole number, which in this case is 6, plus some remainder, which is 1, divided by the dividend, which is 2. So if you think, it works exactly the same as normal like arithmetic division, but just with polynomials in this case. So we can rearrange this to get that f equals qg plus r, where q is quotient. I should probably write that down actually, because that's important. Quotient remainder think that's called a dividend, but I'm not going to write that down because that's a bit embarrassing if I get that wrong. So yeah, f and g are just polynomials. Yeah. One thing that's also very important to know is that for like any polynomial division, f and g, there is only one possible value of q. I'll write that down because that's important as well. There's one possible value, and there is only one possible value of r. Okay, and to prove that there is only one possible value of q and one possible value of r, what I am going to do is I'm going to assume that there are two possible values of q and more than one possible value of q and more than one possible value of r. So, assume, I'm not going to write the whole thing down, but just assume that there are two possible values of q and two possible values of r. This means that for any polynomial f and any polynomial g, f is equal to q1 times g. Oh no, sorry. F is equal to q1. Flip, why do I keep forgetting this? Yeah, it is q1 times g plus r. Say that's r1 as well, actually. But by our assumption that there are two possible values, f is also equal to q2 times g. Remember, g is the same, because we're dividing the same polynomials, plus r2. So, because f is equal to f, we can set these two things here equal to each other. So let's do that. Let's put that down here. Put that down here as well. And those are equal to each other. So what we're going to do is, well, just looking at this, we can see that both of them have a term with g in it. So we're going to move the term with the g in it, which is, in this case, on the right-hand side is q2g, or q sub 2g. We're going to move that to the left-hand side by subtracting it. So we're going to do q1g minus q2g plus r1 equals r2. Now we can factorize this part here. So that g times q1 minus q2 plus r1 is equal to r2. Well, this is interesting. So first thing that we're going to do is let's state what we know. I haven't memorized the proof for this yet, so you don't really need to memorize proofs, you just need to understand them. So let's work with what we know. So what do we know? We know that the degree of g is less than the degree of f. Okay, so we know that, actually f isn't really relevant here, so that does not matter at all. But what we do know for sure is that the degree of r is less than the degree of g. So that's what we know for sure. And what we also know is that the degree of... Actually, let's move this r1 to the other side by subtracting it. So we can say minus r1, and then r1 has also been subtracted from the left-hand side, meaning we can take that away completely. So we know that the degree of q1 minus q2 equals maximum value of, or the maximum of the degrees of q1 and q2. But we also know the same thing for the other side, so I'll just write that out. Degree. If you don't understand what I'm writing right now, watch episode 2 of the series and you should understand. Degree r2 minus r1 is equal to max degree of r1, r2. Okay, and yeah, we know that by assumption, R1 and R2 are not equal, and Q1 and Q2 are not equal. So this leaves us with G multiplied by something here, which is, well, the degree of a remainder is obviously less than the degree of a divisor, which means, and, well, since the degree of R2 minus R1, since the degree of the difference of the remainders is equal to the greater one, or is equal to the greater of the degrees of those two polynomials, this is, well, let's say R2 let's say a degree of R2 is greater than the degree of R1. So if degree of R2 is greater than degree R1, then the degree of this is just going to be, so degree of that is equal to R2. Okay, and we know that the degrees of the remainders are always less than the degrees of the divisors, which means that we've got a divisor here multiplied by well, the degree of this thing here is the greater of the degrees of Q1 or Q2. So that means that we've got the total degree of this, as in like this thing we've got going on here, the total degree of that is equal to the degree of G times, the degree of G plus the degree of the greater one of the degrees of Q1 or Q2. And that is obviously going to be greater than the degree of this thing here, since we know that the degree of the remainder is less than the degree of G, right? Or if you think about it another way, if we divide both sides by Q1 minus Q2, R2 minus R1 over Q1 minus Q2 equals G, we know that the degree of any remainder is always going to be less than the degree of the divisor, which in this case is G. So since degree of this side is greater than the degree of this side, that means they're not equal, which is a contradiction. Moreover, it's not only that, but also since we're dividing, sorry, I should make that clearer, that's a 2. Since we're dividing by a polynomial, the degree of this whole thing is going to be even smaller than the degree of R2 minus R1, which further supports our case. So that's a contradiction, which means that there cannot be more than one distinct remainder and quotient for any polynomial division f divided by g. So to summarize, what we've covered so far, we've covered multiplication of large polynomials, long division here, and we've covered this general formula thing, and why there is only one for any polynomial division f over g. There is one distinct, actually I'm not going to write it down, that's too long. There is one distinct remainder and there is one distinct quotient for every polynomial division. That's what we've covered. We've proved that. I hope that made sense. Sorry if I yap too much. I do like to talk, so maybe I talk too much. I don't know. If you have any feedback, please leave it in the comments. I'd appreciate that a lot. Hope you enjoyed. Bye bye.